Hello guys, you're welcome to my channel, and today we are going to try and then solve some PDEs. Um, Not necessarily the PDEs that are widely known, the transport equation, the diffusion equation. That's not what we are going to talk about. You're just going to talk of how to generally solve PDEs, okay? And this doesn't apply to every PDE, but it's just going to give us some kind of idea of how PDEs really uh, are solved. The general ones, the most general ones, okay? So let's go back to ODE. For instance, if I'm given um, a differential equation of this sort, of this form, u prime plus u equals 0, then there are two ways of solving this. The first one, you can use the characteristic equation, and that's going to be r plus 1 is equal to 0. And then you have r to be equal to negative 1. And then you can see that u of t is just going to be a constant, an arbitrary constant, multiplying e to the power minus t, okay? Or you can solve it by, doing, you have u prime being equal to negative u, and then you can have, du divided by, oh, let me put it this way. Oh my bad, u prime divided by u being equal to negative 1. And then, when you find the integral of this, the integral of u prime divided by u dx, no, dt, that's going to be equal to negative of the integral of, dt. And this is going to be the ln or ln of u of t, right? And that should be equal to negative t plus c. So u of t is just going to be some b e to the power negative t. Okay, so that's how it's done. That's also another method. And there is also another method. You can use the integrating factor. You know that the integrating factor is just going to be e to the, the integral of the coefficient of u here. That is just 1. So dt, and that's just going to be e to the power t. And then you have e to the t. You're just going to multiply the whole equation by that, the integrating factor. So you're going to have e to the power t u prime plus u et being equal to 0. And then you can write to the left hand side as a total or a complete derivative. That's just going to be e to the tu being equal to 0. And then you can see that e to the tu is just a constant. When you try to, find a integral on both sides, when you multiply through by the dt, you try to integrate both sides. This is what you're going to get. And u of t is just going to be c e to the negative t. Okay, so these are ways of solving ordinary differential equations. Now, the only difference between this and a partial differential equation generally is that these arbitrary constants here are going to be arbitrary functions in the PDEs. Okay, so you know that PDE, or in a PDE, the physical quantity depends on more than one variable. Okay, so if you're doing any integral with respect to one variable, the arbitrary, in the case of ordinary differential equation, the arbitrary constants become arbitrary functions of the other variable. Okay, so let me not waste too much time. Let's just go into an example. For instance, let me just divide this pretty quick. You're taking the PDE variant of that. Okay, so we have ux plus u is equal to 0. And then here we have our u to be a function of xy. Okay, so if u is a function of xy, then this equation here is a partial differential equation because you are only differentiating u with respect to x. Okay, so I'm just going to try and then use the integrating factor thing. So my integrating factor here is just going to be e to the integral of 1, that's the coefficient of u, dx. Okay, and that's just going to be e to the x, right? And what happens? I'm just going to multiply the whole equation by that. So I have e to the x u x plus e to the x u is equal to 0. Okay, Then I can write this as a partial derivative. Note that this is going to be a partial derivative because u is a function of x and y. So partial derivative of e to the x and u, and that should be equal to 0. And now you have e to the x u being equal to 0 del x. Ooh, I didn't bring del that. Now we can integrate both sides, or we can integrate both sides, and we're going to have e to the x u being equal to the integral of 0 del x. Now, since this is a partial integration, you're going to have e to the x u. This is going to be, you know, a constant. It's going to be a constant. It's only when you differentiate a constant that you have a 0, okay? But since this is a function of x and y, it's not just going to be an arbitrary constant. It's going to be an arbitrary function of the other variable. Okay, so you can call it f of y, and then u of xy becomes this f of y e to the negative x. So now comparing this answer to that, the only difference is that the c you have here is an f of y. Okay, so generally, if you are solving partial differential equations, the arbitrary constants in the sense of ordinary differential equations become, you know, arbitrary functions of the other variables. Okay, so let's pick another example, and I'm just gonna stop it here, and then in our next video we're going to strictly talk about the first order differential equations, how to solve them. Okay, so in the next example I have u x y is equal to 0. This is what we want to solve. Okay, so we have the physical quantity u being differentiated, is differentiated with respect to x and y at the same time. I can rewrite this as ux or y being equal to 0. Okay, then this is the same as del ux del y is equal to 0. So I have del ux being equal to 0 del y. So we've seen this before, that you're going to have ux being equal to the integral of 0 del y, and this is going to be ux. Since you're integrating this one with respect to y, you're going to have an arbitrary function of x. Okay, now we want to integrate this one with respect to x too. So we're going to have the integral of ux. Oh, let me write it this way. Del u del x. That should be alright, so we are integrating this one with respect to x, right? And that should be equal to, wait, what am I doing? Okay, so this is going to be equal to the integral of f of x, you know, del x, right? And now this is going to be, this cancels that, and the integral cancels the partial derivative, so you're going to have u of xy being equal to, now f is a function of x already, so I'm going to call that integral a big F of x, or capital F of x, because it's a function of x already. Okay, now I'm supposed to add an arbitrary constant if it was an ODE, but now since this is a PDE, the arbitrary constant here becomes an arbitrary function of the other variable, and that's it. So this means that any partial differential equation of this form, where you have, you know, the physical quantity having a derivative of all the variables, or two of both, the u is a function of x and y, and then you have u being differentiated with respect to x and y at the same time, it is always going to be the sum of arbitrary functions of x and y. Okay, so this is what's basically going on. So if you have any variant of an ODE, or if you have any ODE, the solution, the general solution, which has, you know, arbitrary constants, in the sense of PDEs, the arbitrary constants become arbitrary functions. Okay, so that's just a basic concept when it comes to trying to solve PDEs. But this, You know, in trying to solve this, there is this kind of, it seems too easy to solve these ones, but there are specific types of PDEs that cannot be solved these ways. Like, they cannot be solved going through these kinds of processes. Okay, and we're going to talk about them in the next video. So the first one is going to be the transport differential equation, or transport PDE, and then we're going to see how we solve that kind of partial differential equation. We also talk about the diffusion equation. We will talk also about the wave equation, and then how to solve all of those ones. Okay, all right, so see you in the next video.